Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. We are in the week 10 and today is the last session for this particular week. And so far we have seen a theoretical concept of autoencoders and variational autoencoders. Today we will see the hands-on implementation of autoencoders. If you recall the concept from our second session in this particular week, we had seen the types of autoencoders. In that we had seen the shallow autoencoders, we have seen deep autoencoders, then we had seen the theoretical concept of CNN based autoencoders and denoising autoencoders. These are four different types of autoencoders that we had seen in the second session of this particular week. Today we will see the hands-on implementation. More specifically, we will be looking into CNN based and denoising autoencoders. So let us get started. So here you can see we have an conventional or CNN based autoencoders, and what is the first step, since we are dealing with an images. So definitely, or CNN based autoencoders, images should be passed as an input. So what is the first step? The first step is all the necessary packages has to be imported. So here you can able to see. In the first you are because we are using Keras TensorFlow. So the first step is import TensorFlow, and in short we are calling it as TF. So import TensorFlow as a TF. Then because we are using a standard data set, so which is an handwritten digit data set, or it can be an fashion MNIST fashion data set. So here for this particular example, we are taking an fashion MNIST data set, MNIST data set. So because it is a standard one, so under TensorFlow all these data sets are part of. So because we are downloading one standard data set, we are importing a TensorFlow data set as TFDS. So TFDS is a TensorFlow data set, and why is that this particular line is important? Because we are using an inbuilt a standard data set, a data set which is a part of the TensorFlow. So therefore we require this particular line, and then numpy as NP in order to do some numerical operations, and then for visualization we require matplotlib, and therefore we are importing matplotlib.pyplot as PLT. So all these four are the necessary packages that are required before we start the actual implementation. And next, second, once we import the necessary packages, the next step is you have to actually take the data, or you have to download the data. So you see how is this part of code is written. So because we are using an fashion data set for this particular implementation, so the very first step is from TFDS, that is from TensorFlow data set, we have to load fashion MNIST data set. So under this TensorFlow data set, we have multiple different data sets. So in that, more specifically, what is that data that we want to use, that name has to be written here. So fashion underscore MNIST is the name of the data set. Where is this data set present? The data set is present in this TensorFlow data set, TFDS. So the first step is you have to load. So we know that whenever we are loading the data set will have the training, and then the data set will have even the testing part. So now from this data set, what are we taking? We are taking the training part of the data. So, we are writing a split is equal to train because we are taking the training data set. Now, as supervised equal to true, what is the meaning of this? It is a fashion data set which has both image as well as the label. It has both data as well as the label associated with it. So, because we are writing as underscore supervised equal to true, meaning we are taking both image as well as the label associated with that particular image. Now, you can ask the question, or you may be getting a question, because we are dealing with autoencoder, where is the question of a label? Although we are using labels, but we are taking the labels, nowhere we will be using a label in our program. You will be seeing that shortly. So, what is that we are doing? We are now taking the training data. So, the entire training data is assigned to train underscore data set. Now, whatever the images that are present in this train underscore data set, you are calling a function map underscore image. So, let us go back and then see what exactly is a map underscore image. Yeah, here is a function map underscore image. Now, what is that we are passing to this function? We are passing both image as well as label to this particular function. Now, from where did we get the labels? You remember as a supervised equal to true, because we have mentioned it as true, we are getting labels as well. So, for this function we are passing two parameters, one is image, second is label. Then what are we doing? From TensorFlow there is a function called cast, which is a typecasting. Then all the images which are present in train underscore data set, all those images we are converting it into a float type. Now, initially what will be the values? Here the image has a pixel value between 0 to 255. So, all these values are integer values. Now, intentionally we are converting them into a float point. For example, if there is a pixel of 127, now we are converting that into 127.0. If there is a pixel with 255, then we are converting that pixel to 255.0. Okay. So, what is this particular line doing? This line is responsible for converting the pixel values which are in integer to a pixel values of a float type. So, therefore, you see data type what is being specified here is a float, and all the images we are, whatever the image that you are passing here, all those images we are typecasting. Then we are storing the result back into a variable image only. Now, the next step is, why did we do this? Because we are now normalizing the data between 0 to 255 to 0 to 1. Therefore, the next step is you are dividing every of the pixel value with 255.0. When you divide each with this decimal number 255.0, and when you divide, definitely you will be getting an floating point number only. And why floating point? Because even in the image, every of the pixel value we have already typecasted back to a float. So, float divide with the float, we are getting some value, and that is stored back into an image. And you see, end of this particular function map underscore image, end of this function, what are we returning? We are returning image. So, even though we have used label from supervised, as supervised, we have made it as a true and we have taken the label, but nowhere we are using this particular label. Why we are not using? Because we are implementing an autoencoders, and autoencoders are primarily an unsupervised learning. For unsupervised learning, we do not require the labels. Therefore, what we will return, this function returns image only. So, this is what this particular line is doing. Now, see the third line what we are doing, I will just explain you with an diagrammatic representation, and then we will come back to this particular line. So far what we have done, we have taken the data set and more specifically we have taken a trained data set, and then we have normalized the data. We have first converted that into floating point, and then we have divided each of the pixel with 255, so that we are scaling the values from 0 to 255 to 0 to 1. Now, in fashion MNS data set, we have 60,000 samples for training, 10,000 samples for testing. Now, when we want to train, we cannot pass all the 60,000 images at a time. We cannot do that because computationally it is very expensive. Therefore, what is that we are doing? We are defining the batch size. So, what is the batch size we have defined? The batch size is 128. This number 128 is an hyperparameter. You can change this number according to the convenience. So, 128 is the number that we have fixed here. And there is an shuffle buffer size 1024. Now, why is that we are using this shuffle is, now you just see, if at all if we have 60,000 images, what if the images are stored in this fashion? First 100 images, maybe it is shoes, the next 100 images, maybe it is a coat, next 100 images, maybe it is an t-shirt, next 100 images, maybe pant. What if it is being stored in a particular format? Then is it not a kind of a bias that we are introducing? So, because of this, we don't want the model to have an data in a sequence. So, therefore, we want to shuffle the data. So, and what is the buffer size? Buffer size is a small memory where we are going to keep 1024 images, and what we are going to do, that we will see here. So, see here, first we are going to start with the 60,000 training images, and what is the first step? Because the memory, the buffer size that we have taken here is 1024. Out of 60,000, we will first load the 1024 images into the buffer. So, how does the buffer looks like? The buffer now looks like image 1, image 2, image 3, and so on up to 1024 images are stored. Where these 1024 images are stored, it is stored in a buffer. And what is this 1024? It is just one number. And from the 60,000, 1024 images, if you are taking, remaining 58,976 images are waiting. We are yet to process these images. So, 58,976 images are waiting. So, which are those images? If 1024 images are taken, then 1025th image onwards is remaining. Then what we are going to do, the batch size what we have fixed here is 128. So, now randomly we are going to pick 128 images from this buffer. So, randomly pick 128 images from the buffer. Then how many images will be left out in the buffer? The buffer size is 1024. In that 128 images, if we have picked, the remaining are 896. So, let it be. Where these images are, they are now in the buffer. Okay. So, randomly how do we select? So, from this first 1024, randomly you will shuffle and pick 128. So, it can be image 7, image 999, image 45, image 512. It can be any up to 1024th number. So, 128 images we have picked. Remaining 896 images are left out in the buffer. Now, you will load the next 128 images into the buffer. Now, when you load the next 28 images from the data set into the buffer, then where you are going to add, already we have some 896 images are already stored in the buffer. To that you are adding another 128. So, like this, how long we are going to repeat it? Obviously, until we complete that entire 60,000 images. So, how many such batches you will repeat so that all 60,000 images will be completed? What is the math behind? Can you recall? So, what is the training sample size? We have 60,000. What is the batch size that we have fixed? 128. So, 60,000 divided by 128, we get somewhere around 468.75. So, take it to the next higher number, it is 469. 469 batches you will be repeating it to cover your entire 60,000 images. So, this is what is written in this particular line. Can you able to see this? So, we are first we shuffle the entire, and what is the shuffle size here? 1024. Then from that you are going to pick 128 images, and you will repeat this. How long you will repeat it? Until you complete all the samples that are stored in our that is from our training data. So, this is what is the this particular explanation this line is doing. Next, so every image which is stored in the data set, we are going to normalize it. So, the same thing you will now repeat for a test data also, and for a test samples you will take, and here also you will be passing them, because you have to normalize the test data also. But what is the only one change? Here when we are taking you are now, once the model is well trained, these test samples are used only for testing the model. So, we need not have to shuffle those images. Therefore, in this particular line you will see that shuffle this part is not there for a test image. So far what have we done? We have loaded the data, and then we have normalized the data. And what data we have normalized? We have normalized only the training data. So, execute this particular cell so that all the images have been downloaded, and all the images have been prepared to pass it to our model. So, now what model we are building? Since the data set here is an image data set, so definitely the model that we are building should be something related to CNN based model only. So, what we are now using? We are using an convolutional autoencoders. So, this is the architecture that we have built for convolutional one. I am just showing an example here as 8, which is an handwritten one, but the data set that we have taken here is a fashion data set only. So, we are passing some input. I am just showing you the architecture. So, we are taking an input, and the input is being passed to two layers of convolution. Then towards the end of the convolution, we are going to get an latent representation, and this latent representation or latent space is passed to an decoder part. So, let us see how we have to write a code for this particular architecture. So, here is the code that is being written. First, we are calling build underscore models function. So, there is a function that we have written which is a build underscore model. So, what this build underscore model, the control will go to the function call. So, here we are taking an input image of size 28, 28, 1. What is the meaning of this? The height is 28, the width is 28, and the channel is 1. Why channel is 1? Because it is an grayscale, or it can be a binary image. That is the meaning that the channel is 1. So, we have defined an input, and it is assigned to a variable inputs. So, this inputs is now passed to an conv underscore autoencoder function. So, now we have to, the control will go to this particular function conv underscore autoencoder. So, let us go back and then see what exactly is a conv underscore autoencoder. here is a function where we have written the actual logic, the encoder, latent space, and then the decoder. For this, an input is being passed. What is the first step? The first step is a convolutional layer. So conv 2D, we have called 64, we have taken 64 kernels, each kernel of size 3 cross 3. Activation function used is ReLU, padding equal to same, and for this what we are passing? We are passing the input. So now by doing this, what was the original size? It is 28, 28 to 1. So from there, because you are using 64 kernels, by the end of this calculation, is it not we get 28 to 28 to 64? So that is what is written even in the image as well. Can you see here? It is 28 to 28 to 64. Input is 1, from input you have converted to 64. So let's go on. Then once the convolution operation is done, the next is pooling. So what is the intention, what is the responsibility of pooling? It is a downsampling technique. It is now going to retain only the most important features. So here you have downsampled to exactly by half, because 2 cross 2, the sliding is 2 cross 2. Padding equal to same, and max pooling operation is done on what? Definitely the output of the convolution operation. So the output of convolution operation is stored in this particular variable. Therefore this variable is passed as an input to this max pooling. So what was the output size by end of this convolution operation? It was 28 to 28 to 64. Now when you apply it to pooling, you are dividing it by half. So the 28 to 28 will now be exactly half, will be 14, 14, 64. Okay, I hope you are understanding. This is the concept from our week 3, right? So now again we are repeating one more convolution operation. So now this time what will be the input for this convolution operation? Obviously whatever is the output of pooling. So it is 14, 14, 16, 14 cross 14 cross 64 is passed as an input to this convolution operation. Now to this convolution, how many kernels we are using? 128 kernels we are using. So when we are using 128 kernels, we are going to get 128 feature maps. Therefore you see what will be the size? The size here is, because the padding is same, whatever the input size that you are passing, it is the same input that is retained. So what is the input that we are passing? 14, 14, 64 is being passed as an input, and when it is applied to 128 kernels, we get 14, 14, 128. That's what is shown even in the image also. It is 14, 14, 128. So I hope this is clear. So once this is done, it is the resultant of this is stored in encoder underscore conv2, because it's a second layer of convolution. That is passed as an input to an max pooling. So here again you see the max pooling size is 2 cross 2. Which means it is going to reduce by half. So what was the input that was passed? 14, 64. By passing it to a convolution, it turned into 14, 14, 128. Now when that is passed to max pooling, the output will be, it is reducing by half. So which means 14, 14 will now become 7 cross 7. That's where it is 7 cross 7, and the number of such feature maps will be the same, that is 128. Now that is given to an encoder. That is now passed to an last convolution layer. It is passed to a last convolution layer. So what is the input that is passed? 7 cross 7 cross 128. That is passed as an input to the convolution operation, and this is the last layer. If this is the last layer, definitely whatever is the output of this layer will be the latent space, right? So now here how many kernels that we are using? 256 kernels we are using. Therefore, the size now will be 7 cross 7 cross 256. Because the padding is the same, whatever is the input size, you will retain the same input. Before the input what was passed is 7 cross 7, therefore, here also you still have 7 cross 7, because it is 256 kernels, we are getting 256 feature maps. So, this is what is our latent space. So, when we go back to our diagram, it is 7 cross 7 cross 256. This is our latent representation. Now, with this we have taken the most important features. Now, when you go back and then understand the theory behind autoencoders, so definitely it is a compressed version. Latent representation is a compressed version of our input. Now, that is now passed to a decoder. What is the role of a decoder? Decoder has to now reconstruct the input. If it has to reconstruct the input, so input original size is 28 to 28 to 1. But by the time you came here, it is 7 cross 7. So, now the very first step is we have to upsample it. So, now from theory concept recall, so we will do upsampling and then we will do a convolution operation. So, that is what is a decoder part. So, upsampling and convolution. So, you see at the decoder side, what we are doing is first we are doing an upsampling. What was the input that was passed here? The input was 7 cross 7 and we had passed 256, right? Yeah. So, it is 7 256 is passed as an input. So, now when we do upsampling, upsampling is a technique which is used to increase the size. So, 7 cross 7, now because we have used 2 cross 2 here, it is now changing from 7 cross 7, we are now getting to 14 cross 14. So, 7 cross 7 has now changed to 14 cross 14. We are nowhere dealing with the feature maps here. So, the feature maps will be still 256 only. Now, this is stored in an variable decoder upsampling. Now, that is passed as an input to a convolution operation. So, here you are doing a conv 2D and the number of kernels that we are using is 128. Therefore, at the end of this, whatever is the output that we have obtained, that is passed as an input for this operation conv 2D. So, conv 2D, since the number of kernels we have used here is 128, therefore, the size now becomes 14 14 128. The result is stored in this conv 1. Now, that is passed again to upsampling. Why we are doing upsampling? Because ultimate aim is to reconstruct back. If it has to reconstruct data back, then we should get as 28 28. What are we now? Where are we now? We are now with 14 cross 14. So, again you pass it to upsampling and the size here is 2 cross 2. Therefore, from 14 we are getting 28 to 28. So, have we reached back to our input size? Answer is yes. But look at how many number of features channels are there. We have 128 such a feature maps are there. So, that you are now passing to 64. Therefore, the output will be 28 to 28 to 64. So, go back and then see the diagram. We have now reached to this part 28 28 to 64. Have we reconstructed the data back? Answer is no. Why? Because our input is 28 28 1. This is our input, size is 28 28 1. So, there is no way that we can have 28 28 64. So, what we are doing in order to reduce, so we are now passing it to an conv 2D layer where we are using one kernel. Because we are using one such a kernel, the input what is being passed was 28 to 28 128 is now changed to 28 28 1. That is our reconstruction. Now, if you recall from our concept, activation is a sigmoid, not because we are doing some classification problem. Can you recall why exactly activation equal to sigmoid here? The answer is we have divided each of the pixel values with the 255. When we divide each of the pixel values with the 255, ultimately the values are ranging between 0 and 1. Therefore, we have used an activation as a sigmoid here. So, what is that output this function has to return? This function is returning we want the latent representation and we want the reconstructed output. So, latent this is the one that we are taking. Latent, we are taking this and we are also taking this reconstruction. So, this function is returning these two data or these two parameters. Now, so why did we reach there? Because this function has called. So, now latent and reconstruction, when it is assigned back to this function, it is now stored in a variable latent output and reconstructed output. So, now our result is stored in latent output and reconstructed output. So, now what we are doing? We are now building an end-to-end model. So, we are for a complete autoencoder, what is that the flow? You will pass the input and then you will get the reconstructed output. So, this is the complete autoencoder. So, we are building an autoencoder model. For this autoencoder, we are passing the inputs, which is 28, 28, 1, and what we are going to get towards the end, we are going to get that reconstructed output. So, we are now building a model for a it's a graphical representation where we are stitching all of these together. So, inputs and the reconstructed output will make an autoencoder. Now, what is only encoder part? Encoder, is it not just input and then the latent, till the latent space is the encoder. So, we are passing inputs and we are passing the latent output. This is an encoder model. Why are we doing this? Because our next step is we have to compile this model and we have to train this model. Therefore, we have brought everything together. So, from TensorFlow, Keras, we have a model, and to this model we are passing input and reconstructed output. This is an encoder and autoencoder. Then input and latent space, we call it as an encoder. So, now this model build models, what is this function returning? This function is returning these two variables, autoencoder model and encoder model. I hope this is clear to us. So, the next step is just print the summary, autoencoder underscore model dot summary and encoder underscore model dot summary. You will be able to see. Now, you can ask the question, what is this name equal to? Is it compulsory that to write? Absolutely no, it is just to print here. We have written those names. So, the next step here is you have to compile and then we have to train the model. So, what is that we want to compile? Autoencoder, that is the complete model, right? So, autoencoder underscore model has to be compiled. So, model dot compile, the optimizer that is used here is Adam and the loss function used here is binary cross entropy loss. And here model dot fit, what model? Autoencoder underscore model dot fit. For this we are passing the training data set and steps per epochs train underscore steps. So, how do we get train underscore steps? Just some time back we have seen where we will take the samples divided by the batch size. So, we will the training sample size is 60,000 and then batch size is 128. Similar way, so for test data set is passed to a validation data and validation steps here is once again 60,000 divided by 128. So, and how many epochs we are running? Just for learning sake, here I am running it for one epoch, but otherwise when you are applying it for any of the real time applications, you have to run for a sufficiently good number of epochs. So, what we have done here, we have compiled the model and we have trained our model. So once this is done, this is so with this we have actually completed the model training. Now the next is just visualization of our result. So how is that we are can you able to see here? This is our original input. The first row what you are seeing is the original input, and the second what you are seeing is the latent representation, and the third one is the reconstructed data. So what we have taken is a fashion data set. Therefore you will be able to see all the inputs are related to the fashion products only, and we know that latent representation is something which is not understandable by humans. It is a compressed version of an input. So this is a latent representation, and this is the output reconstructed data. So now we want to visualize this, right? So because we want to visualize, now we are writing the two functions. So which are those two functions? These are the two functions which are actually responsible for printing the output. So let us see how it is doing. First, in order, so your model is well trained. After the model is trained, now you want to test the model. So for testing, you are taking one batch of data. So take of one is one batch of data that is stored in the test underscore data set. Now here all the images which are stored in the test underscore data set, you are converting them into as NumPy. So what we are doing, you are taking all of these, and then you are storing these images in a regular format which a computer can understand. It is an NumPy format. So from TFDS as dot as a NumPy, take all these images which are stored in the test underscore data set and convert them into a NumPy. So and we are going to get the resultant is stored in these variables. In that input underscore image is now assigned to one variable. Now we want to print just 10 images, that is sufficient. So we have taken the indices up to 10. So now whatever is the output underscore samples, because the input data is stored in this variable. Now from this take all those 10 images, store it in this particular variable, and reshape them, arrange them properly. How is that you are arranging? You have taken 10 images, and each image is of size 28 cross 28, and there is one such channel. So we have, it is all just for a convenient sake, or we are preparing the samples of 10 batch of 10 images. Now those 10 images are now stored in conv underscore output underscore samples. That is passed, and you are asking the model to predict. Which model? Encoder underscore model. Why encoder underscore model? Why not autoencoder? Because first we require a latent space, right? Encoder model only will give us the latent space. So pass the encoder underscore model, use this encoder underscore model and predict, so that you now have the encoded data. So this encoded data, you are taking the mean of it. Why? Because encoder it has given totally 256 channels, right? So we don't want all those 256 to be displayed. So we will take the average of all those, and then just one viewable image is sufficient for us. Therefore, take the mean of this encoded and store it in encoded for display. Then take these samples, now pass it to an autoencoder, therefore we get the reconstructed output. Then call the display function. Display is the function which is, for this you are passing the original input. This has the original input, this has the latent representation, and this has the reconstructed output. So all that is passed to this display function. So control will go back to the display function. So display result. So to this display result, whatever are the 3 parameters, it is assigned to its associated, its respective variables here, and then the total size here is 15 5, that is width is 15 5 height. Then you are displaying the images row wise. Display one row. For the first time you are displaying all the input images. So display input images, and the location where it has to display is 0th location, and the shape here is 28 28. Then second, you are displaying the latent representation and the location where it has to start and what is its shape, and the third one is reconstructed output, then where it has to start and what is the shape of it. So now the control will go back to display one row. So here is the function where it is a display one row. If you see, you will take all the images that you want to display one by one, and the meaning of this 3 10 offset, what exactly meaning, what exactly is this meaning is, now 3 is at the output we have 3 such rows. The very first row is for input, second row is for the latent representation, and the third row is for the reconstructed output. So 3, and 10 is the offset where it has to start. I mean, I'm sorry, 10 here is the columns, 10 such values or images we are displaying, and offset plus IDX plus 1. So let us see, for the first time what we have passed 0. So when 0 is passed here, offset value is 0 plus IDX here images one by one we will be taking, and its index value will be 0 plus 1, 0 plus 0 plus 1, which means at the position 1 the first image is displayed. Then second IDX value will be 1. So it is 0 plus 1 will be 2. So in the second position you are going to put the second photo or second image. Then IDX will be 3. Then 0 plus IDX will be 2. 0 plus 2 plus 1 will be 3. In the third position you are going to place the next image. So like this, how many you are going to place? For the first you are going to place from 1 to, you are going to place from 1 2 3 4 5 6 7 8 9 10. Okay. So now let us see what will happen for the second. Here offset is 10. Because the offset is 10, so I mean the position what you are passing here is 10, right? So definitely the offset value here is 10. So 10 plus IDX value will be 0 for the next iteration. So 10 plus 0 plus 1, it is 11. So next time at the position 11 you are going to place the first latent representation. Again when you go back, IDX value will be 1. So 10 plus 1 it is 12. So at the position 12 you are going to place the next. So this is how these two functions are mainly used for an representation. So this is all about the CNN based autoencoders. We have for learning sake, for the benefit of user, we have also shown you how to implement the denoising autoencoder. So here denoising autoencoder, the entire program remained the same. So here you see the how the output is. You have lot of denoising noisy images, then the latent representation, and once you denoise it, how is the original, how that output looks like. So for this I am just showing you how to create this noisy image. So here is the function that is used to create a noisy image. So here is that the function. So we will understand this numerically. So let's go back. let us assume the image size, just for understanding I am taking a smaller size image. Let us assume the image size is 2 cross 2. So, let us assume this is one image. Then we are taking a noise factor. Let us assume the noise factor here is 0.5. This is a noise factor. Then randomly we are generating the noise from a Gaussian, we are generating a Gaussian noise whose mean is 0, standard deviation is 1. So, since the input size is 2 cross 2, the noise size is also 2 cross 2. Then the noise factor is multiplied with this noise. So, 0.5 is multiplied with this noise. So, 0.5 into 0.30, 0.5 into minus 1.20, you multiply 0.5 with all the values here. What did we do? We have taken an input and then we have taken a noise factor here, and then we have generated a noise. And how did we generated the noise? We have generated a Gaussian noise whose mean is 0, standard deviation is 1. Why did we take 2 cross 2 only? Because the input size here is 2 cross 2. Therefore, we have taken 2 cross 2 noise and we have multiplied the noise with the noise factor 0.5. Then this noise is added to the image. So, what is our image? Image is 0, this is our image matrix. So, image and then this factor is being added. So, with this the noise is being added to the image. Okay. Now, when you see here there are some pixel values which are greater than 1, therefore, we have to clip it. So, clip and take the range as 0 to 1, any value which is greater than 1 should be clipped. Should be clipped to what? At the most to 1 only. So, here 0.35 is not greater than 1. Here 0.15 no. 1.30 is greater than 1. Therefore, it is clipped back to 1. And 0.35. This is what is the overall concept. So, go back and then see here. We have taken the noise factor as 0.5. This noise factor is being multiplied with randomly generated noise from a normal distribution. How do the system understands how much, what should be the shape of this noise? So, you pass the shape of an image, therefore, whatever is the input shape, the noise also will be of the same shape. That values are getting multiplied with the noise factor, then store it to factor and add it to an image and then clip the values and normalize each of those values, and return is a noisy image and an image. Rest everything is same as the CNN based autoencoders. So, with this we have come to an end of week 10, where in this particular week we have started with autoencoders, variational autoencoders, and then towards the end of the session we are seeing the hands-on implementation of autoencoders. With this, thank you.